Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. We've gotten now to our 7th lecture of the semester, where in this lecture, the focus is going to be on forward kinematics. So that is how a robot can infer the pose of each of its parts. So in this particular slide, we're going to be working up towards the case where this sequential arm could be positioned in space within the robot operating system. And so before we get into the material, let me go ahead and minimize myself so we can all see the slide content. So when we talk about kinematics within robotics, the high-level concept can be summarized really just in a couple of points as shown here. So ultimately the goal for robot kinematics is to consider the following. So in this setup, we're given the structure of a robot arm. So we're told essentially what each part of the robot is, and we're given some information about what structure the robot can take, and we want to then compute two possible results. So the first would be us trying to infer the pose of the end effector of the robot given the current state of each of the joints. And second, then, we might want to be able to infer which joint states are required in order for some desired end effector pose to be taken by the robot. And so these two topics within robot kinematics are referred to as forward kinematics, where we try to compute where the end effector is currently, given the current state of each joint, and inverse kinematics, which was where we try and compute how the joints need to be set such that the end effector will take on some desired pose. And so you might remember from our last lecture is that essentially before we can get into robot kinematics, we need to have a solid foundation of linear algebra. And so if you review lecture 6 from last week, we covered the basic concepts from linear algebra that we'll be needing for forward kinematics. And so I would point you to our lecture 6 recording and also the slides posted on our website. But in addition to that, there are a number of really good resources that you can use to brush up on some of your linear algebra. So one in particular, a really useful resource is the YouTube channel 3 Blue 1 Brown, who has a really nice series on what they call the essence of linear algebra, where they have very, very nice visualizations for the foundational concepts from linear algebra. So this is one tutorial. There's also a number of good texts that the course staff that we can refer you to if you're looking for additional linear algebra review material. But with that, lecture 6, like I mentioned, did cover the foundation that we'll need for this course. And so we should now be ready to move into robot kinematics. So we'll be starting in this lecture with forward kinematics and then working our way towards inverse kinematics. And so one useful framework that we can sort of put this concept of robot kinematics into is our concept of the robot operating system, right? So the focus for this course. And so in particular, where forward kinematics and inverse kinematics fits within this course is shown on this slide. So you might remember we looked at how it is that we're going to be covering a breadth of topics within this course. And so given that they're project-based, so once again, the kind of modules within a robot operating system that we'll be covering are highlighted in the red outlined boxes or the green outlined boxes. And so from lecture 2, we looked at path planning and how robots can move within a essentially like a floor plan space efficiently. Lecture 4, then we looked at how we can physically simulate our environment, our physical environment within a computing device. Lecture 5, we looked at PID control for controlling the actual actuators on a robot. And so this lecture and the next lecture, we're going to be talking about the concepts needed for forward kinematics, leading towards ultimately inverse kinematics, which we'll look at later on in the course. And so one kind of exciting question then that we'll be able to move towards with forward kinematics is this question here. So could our robot potentially build a champagne tower? And so this particular image and this concept actually was worked through by one of the former PhD students from our lab, Jiaming Zhao, who actually did successfully create such a robot. And so in this particular course, we're going to look at how it is we might be able to work towards a robot that could perform such actions as this. So in this particular video, this was taken from some of the work of Zhemeng, where the robot, you'll see, is able to move its end effector in an intelligent manner to ultimately construct the champagne tower on the table then that's shown on the right. And so what's needed for this to be successful is the robot needs to be able to understand where its end effector, so that is the gripper, which actually holds the champagne glasses, where it is within the three-dimensional space that the robot exists within, right? And so that is ultimately what we're going to be working towards as we talk about forward kinematics and inverse kinematics, right? And so in this particular example, right, so the robot wouldn't be able to be successful in manipulating these champagne glasses if the robot didn't understand where its own actuation, where its own end effector was within space. And so with forward kinematics, we're going to be able to model and control any open chain rigid body robot that we can describe. So let's take a look at a few example robots that we could be modeling with this open chain rigid body framework. So to start with, one robot is the SCARA arm, which is shown on this particular slide, which is a robot that has two revolute joints connecting it to its base, and then in addition a prismatic joint which is attached to a gripper that ultimately allows it to perform the manipulation tasks like the one shown in this particular clip. And so we call this an open chain robot in terms of its kinematic structure, because there's no loops within the kinematic model. And so the links in the joints follow this serial chain structure. Similarly, another robot following a structure of a serial chain is the Monoman robot, shown in this video clip, where this particular robot has three revolute joints, allowing it to move within its configuration space, again, as well as an end effector that then allows it to perform a series of manipulation tasks within its environment. Also following this serial chain structure would be some example bipedal robots. So here, for example, was an early biped robot from the MIT Leg Lab, known as the biped hopper, which was able to walk and sort of run through space, as well as perform these acrobatic jumping motions. And so one thing I could point out is that if you're interested in this particular type of robot, I think a really cool extension could be to implement one of these robots in simulation. So once we start working in our kinematic evaluator stencil for projects 3 onward, this simulation of a biped robot will become kind of more familiar, and it really is kind of a cool extension. So if you're interested, this is something that you certainly could pursue. And so this biped hopper robot in particular was a precursor to some of the modern bipedal and quadrupedal robots that we see currently coming out of research and in industry. So here, for example, was the Boston Dynamics Big Dog robot. And once again, this robot follows an open chain kinematic structure. In addition, though, there's also quadcopters that follow this open chain structure, and so there's no actual loops within their kinematic structure. So once again, this is a type of robot that we could be modeling with forward kinematics. And so some of these quadcopter robots have demonstrated some really impressive control. So here's an example from ETH Zurich of a pair of quadcopters cooperating in their control in order to perform this sort of pole passing task. And so what's impressive here is sort of the speed of their control, but also the ability to coordinate in this very complex action. So as we begin to move into forward kinematics, essentially what we're going to be asking is how we can express the parameters of the robot and the state of the robot as an articulated system that will allow us to describe how it is configured within space. And so for this particular course, it's going to come down into to forward kinematics and inverse kinematics implemented as distinct sets of projects. So for projects 3 and 4, we're going to be focusing on forward kinematics, where our goal is going to be to assemble individual robot links into their proper configuration with making up the robot structure. And then in project 4, we're going to then be controlling that robotic structure to still satisfy a valid configuration such that it could perform a dance. And so shown on this slide are the set of robots that we can be working with within our Knievel stencil for projects 3 and 4. And so these are the robots that your code is actually going to be able to configure in space according to forward kinematics. And so one thing that I'll point out that is important for projects 3 and 4, but also is really powerful, is this idea that your code is not going to change dynamically for each one of these robots. Instead, what will happen is you'll implement forward kinematics in such a way that it'll work as a general process such that for any open chain serial robot description that gets passed into your code will be able to execute forward kinematics and assemble the robot correctly. So your code itself won't have to change, which is a really powerful kind of characteristic of the forward kinematics that we'll be implementing. So if we go back and consider robot kinematics, here was the summary that we had. And so what we're going to be focusing on for this lecture is just the forward kinematics component. So within forward kinematics, the goal is ultimately to infer the pose of each joint and each link that makes up this serial chain robot within a common frame of reference within this world workspace is what we're going to be calling it. And so as input, or the sort of assumption that we're going to be given, is that we have knowledge of the robot's kinematic definition, the geometry of each link, and the current state of all the joints on the robot. And so given that information as input, in lecture 7, this lecture, we're going to be considering how we can configure the robot based on that information as a stationary structure that's configured. And in the next lecture, lecture 8, we're going to then be discussing how we can incorporate motor motion into that configuration such that the kinematic definition is still satisfied, even with that motor changing the configuration. And so forward kinematics itself, we can think of it as a many-to-one mapping that's going to map the robot configuration to some reachable workspace of the end effector pose. And so there's sort of another way of saying that is that for one particular pose within the workspace, there might be many robot configurations that can reach that particular pose. So that's one useful thing to keep in mind. And so let's start then by defining some notation that we're going to be using throughout this lecture and our discussion of forward kinematics. And so we're going to work through this particular figure, and so we'll start with some notation. So the first is, if we look on the left-hand side of the screen, so we have this global frame. So we're going to denote the global frame by W, and we can think about this as being the sort of origin of the world itself. So it's the origin of all of our 3D space that we sort of share with the robot. Moving towards the right of the slide, we have the base of the robot. So we're going to denote the base link of the robot as existing in frame 0. And then as we move along the robot, each of the links along the robot is going to define its own frame, which are going to be indexed kind of accordingly. So starting with the base being frame 0, then we'll have a link in some frame 1, a link in frame 2, and so forth, up until we get to the end effector on the far right-hand side of the slide, which will exist in this particular robot's case within frame 6. So in addition to that notation, we also have notations describing the transformation between these frames, which we'll denote as capital T, where the subscript denotes the particular link that has been transformed, and then the superscript as the link that the transformation has occurred with respect to. So in this particular slide, so in the middle of the slide, we have this T sub 6 and superscript 0. So this denotes the transformation of the end effector with respect to the base. So it's the transformation from the base frame to the end effector frame. Using these notations, we'll also refer to the full 3D space in the world frame as the workspace of the robot. So if we say the workspace of the robot, or if we say the global frame, that's just talking about the 3D space that the entire system exists within. And so from here then, what we have is our kinematic chain, where we're going to have n plus 1 links connected by n joints, where each of the links has its own coordinate frame. So shown on this particular slide with these red axes at each link denote the origin of each of the links' coordinate frame. And so in addition to this, we have then a joint for connecting each of these links, each of these pairs of links. And this joint is what relates the motion of one link with respect to another link. So we have in this serial chain robot framework what we call a child link of each joint and a parent link of each joint, where the joint motion only affects the child link for each joint. And so in addition, each of these joints will be parameterized by some value q, where q denotes the angle of rotation if it is a revolute joint, or the amount of translation that currently exists in the state of the robot if the joint is prismatic. So to point out some of these links and joints specifically, so we have, for example, on the left-hand side of the screen, we have joint 1 which is showing with that first blue arrow is the axis of rotation for joint 1, where link 1 is a child of joint 1. So link 1 is what will actually be affected by motion of joint 1, whereas link 0, the base of the robot, is the parent of joint 1. And so this same notion of parent and child links for each joint kind of extends as you work your way down the kinematic chain. And so within this then, what we're going to be doing is we're going to be trying to describe each translation that follows within this kinematic chain. So for example, what we want to be able to do is we want to be able to define how link 1 is related to link 0 based on the state of this joint that connects the two together. And so we're going to be doing this using matrix notation to describe either the revolute state or the translational state of each of these joints. In addition, then, we have what we define as the configuration of the robot, which is the state of all of the joints kind of taken together in this kinematic chain. And so the configuration depends kind of on the current state. But if we consider the space of all possible configurations, so this would be like sort of considering each of the current joint states as being a variable, then we'll have the space of all possible configurations that the robot can take based on its kinematic structure. And so what we're trying to do in forward kinematics is we're trying to find a transformation for the end effector with respect to the world frame given the configuration of the robot. And so this transformation is unknown, and so this is what we're trying to compute. And so the reason why this is a little bit challenging at first is the fact that each one of these links, before we've done any computation, considers itself to be the center of the universe, so to speak. So each link considers itself to have its own origin, that it exists kind of within, and it ignores that world workspace or frame of reference. And so what we have to do is we have to transform each of these links from their local origin into this global origin, or into this global coordinate frame, in order for the end effector pose to be positioned properly within the workspace. And so the approach that we're going to take is illustrated in the following way, where we'll consider each of the links to have their origins aligned with the global origin to start, and then we're going to walk through the serial chain, and we're going to sort of one by one transform all of the links together, but then drop off each link one by one at its position in the chain. So for example, so the first thing we're going to do is we're going to transform the base link based on its translation within the world. So you can see we're going to translate all of the links together by this translation, and then we're going to move to link 1, and we're going to transform it according to the joint that it's attached to as its parent joint, where they're going to transform the rest based on link 2 and link 3 and so forth until we've walked through all of the links within this kinematic chain, and we'll end up with the position of the end effector. And so the way then that we can think about this is we're kind of composing these transformations of each of the links together until we've reached the end effector link, where the result is what we will have been after. So we'll have computed this transformation of n, in this case 6, with respect to the world, as being this sequence of transformations. And so once we've computed this transformation, we can then apply it to any point within the end effector's frame of reference to actually know where that point exists within the 3D workspace. And so the calculation then that we're going to be using is based on these matrix transformations that are applied as a matrix multiplication. And so 2 questions then that we're going to have to answer is first, how do we represent what we call homogeneous transformations? So these are transformations that allow us to apply both rotation and translation in one single matrix multiply. And second, how do we compute the transform to the end effector? So how do we actually compute this value t sub n superscript w? So this ultimately is what is going to be the 2 key processes within forward kinematics. So once again, so the goal is to infer the pose of each joint and each link in this common world workspace, so this common world frame of reference. And so we have to compute these 2 values, and we're going to be assuming that, given as input, we know the geometry of each link, we know the robot's kinematic definition, and we know the current state of all of the joints. And so in lecture 8 then, we're going to come back and consider the joints that can move and how motion in the joints affects the resulting configuration of the robot. But so to start with, for this lecture, we're just going to consider that we have given to us the geometry of each link and the robot's kinematic definition, ignoring motion of the joints. So let's start now by talking about this robot's kinematic definition. So how do we define the kinematics of a robot? Well, traditionally, one technique that has been used in the past quite frequently is what's known as the Denevit-Hartenberg convention. But in this course, and more recently within robotics, there's a format called Universal Robot Description Format for defining the kinematics. And so this URDF convention is what we will be following in this course. And so if you're curious, if you'd like some additional documentation about how URDF is used on sort of physical robot platforms, then I'd recommend you can check out, if you go to ros.org/URDF, where ros.org has documentation for a robot operating system known as Robot Operating Systems, or abbreviated as ROS, which is used very, very commonly within research and industry. And so on this particular page, they have a very thorough documentation about how ROS defines URDF for robots using ROS.
But in this course, we're going to be using a slightly simplified version of this format. But once again, so URDF stands for Unified Robot Description Format, and so it's a way for us to describe the kinematic structure of robots in a very general form, so that the description can apply to sort of any kinematic structure that we might want to work with our robot operating system. And so the way that this format is defined is sort of as follows. So to start with, Ross uses a URDF to define the kinematics of this robot as it's an articulated structure, where the kinematics is expressed as a tree data structure that represents each link as a node within the tree, and then the joints which transform the links with respect to one another are expressed as edges within the tree. And so the nice property about this particular format is it's very amenable to what's called matrix stack recursion, which is what we're going to be looking at. And so from a more kind of technical, or from a kind of like forward-looking point of view, the way that we're actually going to implement forward kinematics is based on this matrix stack recursion technique, where we'll essentially process through the tree, kind of iterate down the branches of the tree, and along the way we'll perform matrix operations to actually perform the forward kinematics. And so this is what we refer to by matrix stack recursion. It's just this process of kind of flowing through the tree and performing these matrix operations, which we'll talk about in more detail in the upcoming slides. And so in addition, this URDF tree is specified in an XML format, where you have nested joint tags to express the actual branches within the tree. So let's take a look at an example of what a test example of what URDF would look like for a robotic structure. So the code here on the right is example XML that defines this test robot within the URDF format. And so this particular robot would look something like this. And so what we're going to do now is we're going to step through this URDF and sort of show how this robotic structure on the left gets constructed or is represented by the corresponding format on the right. So to start with, the first tag within this URDF format is the sort of empty robot tag. So here all that's specified is the name of the robot, with then all of the contents within this tag, so within the open tag and the closed tag, are what actually defines the remaining links and joints. So to start with, we have this set of links specified. And so for this particular robot, we have 4 links, as shown in the left figure with the highlighted red ovals. And so correspondingly, within our URDF file, we have 4 link tags. And following that, then, we have a set of joint tags, which are used to kind of construct the actual tree. And so within each joint tag, the joints have a name, they have a type for either continuous, or you could have discrete. And then in addition to that, we have the parent link defined for each joint and the child link for each joint. And so the parent and child links then are denoted by their corresponding name as defined in their link tag. So for example, if we look at joint 1, so joint 1 has a parent link of link 1 and a child link of link 2. And so if we look within the tree, what this corresponds to is the branch which goes from link 1 at the root to joint 1 to then link 2. And so that's specified by that first joint tag. And so if you follow then for joint 2 and joint 3, you could see how the second branch gets constructed. So in addition to this just base kind of tree structure then that's defined so far, also within each joint, we define the local frame of reference for that particular joint. So the origin XYZ and RPY. So XYZ would stand for a translation for that joint frame, and RPY then describes a rotation for that corresponding transformation. And so what this looks like is we have essentially an origin field which specifies the transform parameters of each child frame with respect to the parent frame. And so in addition, then, this is what's described by So the final then parameter is this axis field, or this axis tag. And so what this describes is the axis that the degree of freedom for this particular joint can act on with respect to the parent frame. And so, for example, if you have a rotational joint, this axis specifies essentially the vector representing the axis of rotation about which that joint can rotate, again with respect to its parent link's frame of reference. And so I know this is this looks like a lot, so we're gonna step through it, and we're gonna have a lot of examples in this lecture and upcoming lectures to go over these transforms, because this will look if this doesn't look kind of familiar, then it can seem kind of tricky at first, but we will work through it. So within Kineval, so within our stencil, I'll point out a few things that are worth looking at as we start to talk about this URDF format. So the first thing is, if you go to your stencil and you look under the robots directory and you enter into the robots directory, you'll find a set of JavaScript files. And in particular, if you look at the robot_URDF_example.js file, this contains an example of the URDF format which we'll be using in this course, that follows actually the same kinematic structure that we just looked at from that XML format. And so within this, what you'll find is, you can see we define the robot name to be our URDF example, which corresponded in the XML format to be that robot tag with the name test robot. We define then the kind of initial global position of the robot. We define then a base of the robot, which is our link 1, and then we have a set of links for this robot, which corresponded to the XML tags for each of the 4 links. And so once again, so in this course, we're going to be using a JavaScript object to describe the robot. And so this object is sort of taking the place of those XML tags, and it's going to make our lives a little bit easier, so we don't have to worry about parsing that XML. We can just stick within the JavaScript world. So in addition, then, just as like a bit of a kind of quick refresher about JavaScript indexing, so within this robot object that we set up, you could access the links by using dot notation to access the actual property of the robot, which is the set of links, and then you can access each individual link, for example, by using bracket notation to access the individual link that you're trying to access by name. And so in addition to this, because we're going to be using objects, we can actually then traverse the tree as shown in the kind of example on how to access the parent joint of link 2. So the way we'll set up the links will allow us to point back to the actual parent joint of link 2, and then we could point back from the parent joint of link 2 back to its own parent link. And so it'll make more sense with some more examples. But I just want to point this out just to remind ourselves that since we're working within JavaScript, we can treat these objects as we've been doing in projects 1 and 2. So if you sort of look a little bit further down the page, then what you'll see is we have a section where we define the joints of this particular robot. And so for this, once again, we set up the joint property of the robot object as itself a JavaScript object, where then we assign a set of joints to this joints object based on the kinematic structure that we're trying to implement. And so once again, so for this robot, we had 3 joints. And so you can see here we have 3 blocks of code where we specify joint 1, joint 2, and joint 3. And correspondingly, each of these joints, just as we saw in the XML format style, has a parent link, a child link, a origin transformation. So this is the origin with respect to the parent, and we have then the axis of the degree of freedom. And so each of these joints you can see has those properties defined. And so here, for example, is that summary that we just looked at. So we can have the parent and the child links for each joint. We can have the transform parameters for the joint with respect to the parent link frame. So we have an XYZ, which denotes a transformation. We have an RPY to denote a rotation. And then we have the joint axis, which describes the axis of the degree of freedom operating. So this would be the axis of rotation for a revolute joint, or the axis of translation for a prismatic joint. And then, in addition to that, we have a type parameter, which we didn't use in this particular example, but can be added to specify either a revolute joint, a prismatic joint, or what we call a continuous joint, which is a revolute joint that doesn't have any limits of rotation on it. All right, and so once again, since we're in JavaScript, we can treat this joints object as a JavaScript object and access its properties, using dot notation or using bracket notation. Okay, so then the final thing, if you scroll down even like a little bit further within this file, is you'll see that we set up the geometries of the robot. And so I mentioned that that we're going to assume in this class that the geometries of each link are given to us. And so you don't need to worry about this code down here that's setting up the geometries. But if you're curious, what's happening here is we're actually setting up these 3JS geometries, which is what is used ultimately to render our robot within our 3D environment. And so these geometries you can think about as being essentially what's actually going to get shown in our visualization for each link. But again, no need to worry. The only thing that this will be useful for is if you decide to create your own robot description. You can kind of copy and paste some of these geometries to help you with that. Okay, so now that we've looked at the robot's kinematic definition, the next thing that we want to look at is we want to kind of understand this idea of a geometry of each link. And so these geometries are going to be defined very similar to how you would see geometries within computer graphics or computer gaming defined. And so what it's going to come down to essentially is a set of vertices that exist within 3D space, and then connecting those vertices together forms the faces of the geometry. So in this particular house example, the faces of the geometry are sort of the walls of this house. And so to go a little bit deeper into that, so each robot link is going to have a geometry defined for it. And so within this geometry, there's going to be defined a set of three-dimensional vertices. And if we connect the vertices together, we get faces, which form the surface of the geometry that's actually visualized within the simulation. And so these vertices then, so they're 3D points that are defined with respect to the local frame of this particular link. And so in the case of this house example, right, so if we connected, let's say, vertex 0, 1, 2, 3, 4, and then back to 0, we'd have that front face of the house. And then what this would look like in terms, like a little bit more in terms of the kind of technical details, would be what's shown on the right. So this model of this house could be expressed as this set of 10 vertices, each of which has a 3D point, and then could be connected together. And so using this representation, what we can then do is we can then express this link within space based on the location of its vertices, and we can then transform this link within space by transforming the location of the vertices, right? So in this particular case, what's shown here, right, is we can rotate the link, and we can translate the link within this world coordinate frame. So the translation is shown by the fact that the entire link is offset from the global origin, and then the rotation that we saw was illustrating this idea that we can rotate the vertices in order to rotate the corresponding geometry. And so within Knievel, what we're going to ultimately be doing is expressing that same concept of having a set of linked geometries that we can position within the world, and we can transform with respect to one another, according to a similar process. And so what's shown on this slide is just a snapshot from our three-dimensional simulation that we're going to be working in moving forward for projects 3 onward. And so while this particular snapshot is showing the robot before we've done forward kinematics, what we're sort of illustrating here is that we're going to actually be able to visualize a set of geometries within our three-dimensional space, and we're going to be able to position them within the three-dimensional world using these concepts that we're talking about. And so within the code, ultimately the way that we're going to position each of the linked geometries is by specifying a transform, which we call X-form. So we're going to specify an X-form property for each of the links. And so what this X-form ultimately is going to be is it's going to be this matrix that we sort of saw on 2 slides ago that was controlling the rotation and the translation of that specific link. So this matrix A is going to be what is expressed as the X-form property for each link within our simulation. And so just as a quick kind of refresher, the way within JavaScript that we can express matrices is by describing them as an array of an array. So we have this essentially 2-dimensional array structure that allows us to express the elements of the matrix as individual elements within the underlying arrays. So each one of these .xform properties will be a separate array corresponding to that specific transform for that specific link. And as we modify these transforms, we'll be able to change the position of the links and the orientation of the links. So now that we understand how these geometries are defined based on the vertices and the location of the vertices within space, and we can kind of understand how we're going to position these geometries within space, let's focus on exactly how we can represent these transformations. And so the technique that we're going to be using is what's called a homogeneous transformation. So let's look at how it is we can define these transforms. And so to do this, let's start with a simple example, and we'll build up to more complicated examples. And so let's say that we're working with a link that's this rectangular link shown on this slide, and we want to be able to construct the transform such that we can control where this link is positioned within space. So to start with, let's consider how it is we could rotate this 2-dimensional link based on a rotation applied to the 4 vertices that define the link geometry. And so to do this, right, so we'll point out that each of these 4 vertices can be thought of as vectors expressed with respect to the origin of the link, right? So each of these points has an x and a y coordinate, and so when we want to rotate the link, right, what we're going to do, as we saw with that house example, is we're going to rotate each of these vertices. And so in the case of 2D rotation, right, one question that I would sort of pose to you is, if you think back to kind of trigonometry and algebra, how can we rotate these individual vertices based on some known angle of rotation that we want to apply, which we can call theta, where this theta is describing the angle of rotation about an out-of-plane axis. So you can think about an axis of rotation that points kind of out of your screen, centered at the origin. So I'll pause, and you can take a second to try and think of the answer. So So now that you've had a second to think about it, so we can look at the answer, and essentially by just applying trigonometric functions like cosine and sine, in the case of 2D rotation, we can express in closed form how the points x and y for each vertex would be transformed into x prime y prime after applying this rotation. And so the equations are shown on this particular slide if you work through it. And so what we can then observe is that this might look somewhat familiar from the linear algebra refresher that we had, which is that we have essentially two equations and we have two variables that are each expressed within the equations to apply this transformation. And so what that hints at is that we can actually take this transformation and apply it as a matrix multiplication. So those same two equations could be expressed in this matrix multiply that we see here, where we're essentially taking the trigonometric cosine and sine values from the equations, and then we're applying them as a matrix that gets multiplied with the original xy vertex to form the transformed vertex x prime y prime. And so if we instantiate this rotation matrix with a specific angle theta, we'll be able to apply this rotation correspondingly. And so one thing to remember is that this rotation is applied in the counterclockwise fashion. And so that's by convention. And so one way to always remember this idea of rotation in the counterclockwise direction is to remember what's referred to as right-hand rule. And so right-hand rule is a tool that you can use for remembering these properties about rotations. So in particular, the way the right-hand rule works is if you take your right hand and you point it along and you imagine your palm essentially facing along the x-axis, and you curl your fingers in to form a fist, that curl direction is the direction of rotation that corresponds to the axis along which your thumb is pointing. And so within right-hand rule, one thing that's important to remember is that our coordinate system is going to have conventions that are going to control how the rotation is actually defined. And so to make things a little bit kind of confusing, if you have different coordinate systems, then you're going to have to be able to transform between those different coordinate systems. And so this frequently comes up within robotics, where you might have to essentially communicate between different programs which use different coordinate systems, or different algorithms using different coordinate systems. And so it's a useful skill to be able to learn how to do properly. So in this particular course, within our simulator, we're going to be following the coordinate system defined by 3JS, which is shown on the left-hand side. So our x dimension is going to be lateral, our z dimension is going to be forward, and our y dimension is going to be up, or sort of vertical. Whereas robot operating system and a number of other applications within robotics define a slightly different coordinate system, where you have y is the lateral direction, x is the forward direction, and z is the up or vertical direction. And so the reason that we're pointing this out is that for this course, our URDF files are going to be defined in the ROS convention, but our simulator needs to be able to ingest those robot description definitions and then visualize them in the 3JS coordinate system, which is shown on the left. So we're going to have to be able to do this coordinate transformation between these two systems. And so once we get to this point in the project, we will be sure to point out how it is we can do this transformation properly. Okay, so as a quick checkpoint to sort of check your understanding and some of these concepts that we've been talking about, here's a couple questions that you can think about. So maybe you can pause the video here and take a moment to think about these. So now that you've had a chance to think about these, we can go through them. So in the first question, so we're asking, what would the 2D matrix for a rotation by 0 degrees be? And so if you remember some of those trig functions, you can recall that this rotation matrix could be specified as the identity matrix. And in the second question, what is a 2D rotation matrix for a rotation by 90 degrees. Well, this one you can similarly calculate by plugging in 90 degrees to those functions, and you should have a matrix that looks something like the one shown in this particular equation, where this is applying that rotation of 90 degrees as a matrix multiply, as we described in the past set of slides. All right. So the other thing that we can point out about this convention of using matrices to represent rotational transformations, one nice property is that we can actually consider this transformation applied to a set of points as a single matrix multiply operation. So in the case of our 2D rectangular box geometry, we could actually transform all 4 of the vertices using a single matrix multiply, as shown on the lower portion of this slide. So if we expressed each of the vertices of our box geometry as a column of a matrix on the right-hand side, we could then apply our matrix multiply with our rotation matrix to transform all 4 of the vertices in one operation. And so this follows just from the definition of matrix multiply that we saw in the linear algebra refresher. Okay, so now that we've looked at 2D rotation, the next thing we want to talk about is how it is that we can translate our geometries within space. And so it turns out that we can translate geometries. And so let's look at a case of 2D translation. So we'll stay in this world of our box geometry, and let's consider how it is we can actually transform our box by transforming our vertices. So in particular, the way that we can do this is we can apply a translation vector to each dimension of our vertices. So in the case of our box geometry, right, this means we can apply an offset in the dimension x to our x vertex, or to the dimension x of one of the vertices, and we can apply a translation along the y dimension of one of the vertices to form a new transformed vertex x prime and y prime. And so just as very similar to how we applied rotation matrices as very similar to how we applied rotation transformation as a matrix multiplication, we can follow a similar process for translation transformations. So that is, we can express a 2D translation as a matrix multiplication in what's referred to as homogeneous coordinates. So the way that we do this is illustrated on this particular slide here, where we express within the matrix on the right-hand side of this equation, we have our transformation expressed as a 2D translation matrix. And so within this, what you'll see is that we have our offset in the x dimension and our offset in the y dimension as 2 of the elements within the third column of the matrix. And in addition to that, we've expressed our vertex x and y for one of these points as a column vector with 3 elements. And so this additional element within this column matrix is just a unit element, so it's just 1. And by doing this, by taking our 2-dimensional position and expressing it as a 3D vector, where the 2D position is concatenated with a 1, this is what we refer to as homogeneous coordinates. And so the reason that we use this homogeneous coordinates is that it allows us to express the translation in this form of a matrix multiply. And so if you work out what this matrix multiply will do, it'll perform exactly what we expressed on the previous slide, which is we'll form our new point x prime y prime as being simply the x position of the vertex shifted by the translation in the dimension x, so that's d sub x, and y prime will be equal to the original y dimension of our input vertex shifted by the translation d sub y. And so this homogeneous coordinate system is is used very frequently. And again, the nice part about it is it lets us express translation, again, as a matrix operation. So as a quick checkpoint, so to check our understanding, you could pause the video here and see if you can remember what the 2D matrix for a translation by this -1 in the x direction and +2 in the y direction would be. So once you've thought about it, we can look at the answer here. So this particular transformation matrix is shown on this slide here, where we've inserted our translation in the x and our translation in the y within that third column of the matrix. And so if you work out then what the translation of this -3, 2 point would be, you'll find that it is -4, 4 in the output. So to bring these two concepts together, then we have what's referred to as rigid motions, which is related to, you may have heard in other contexts, affine transformations, which include rigid body transformations like rotation and translation, but also shear and other transformations. So for this class, we're just going to be focusing on rigid motions, so translation and rotation, since we'll assume that our robot geometries are rigid body objects. And so these rigid motions can compose rotation and translation together to transform these vertex locations within each robot link. And so the way that we can actually compose these two transformations together is by rotating first and then translating. And so if we look at what that looks like, so if we go back to kind of an example here, so the way that we can compose these transformations is by simply applying multiple matrix multiplies in sequence. And so shown here would be the approach of first rotating, which is the first matrix multiply, using our homogeneous matrix for rotation, and then translating by applying our second matrix multiply, which is the homogeneous transformation matrix for translation that we saw. And so by composing these two transformations together, you could alternatively describe this as a single matrix multiplication, where the rotation component is expressed in the upper 2x2 submatrix, and the translation component of the transformation is expressed along the third column of our matrix. And so this is the really nice property about using homogeneous matrix transformations, is that we can perform both rotation and translation as a single matrix operation. And so these homogeneous transforms that compose rotation and translation are what's referred to as special Euclidean group 2 in the case of in the cases that we've been looking at. And so in this particular case, we could say that this matrix H is an element of this special Euclidean group 2, where it's composed of a 2x2 rotation matrix, which is an element of what's called the special orthogonal group 2. So this is an orthonormal matrix. And in addition, then we have a 2x1 translation component, which is from real 2, so the space of real numbers of dimension 2. And together, this is then what is going to form really the foundation for transformations that we're going to be focusing on in this course. So we're going to be focusing on rotational and translational transformations only. So let's now put this to an example where we're going to try and build up a robot structure called Boxy the Robot. So once again, so this is going to stay in the 2D world for now, and then we'll move to 3D coming up. So to start with, so here's our robot, and within the robot, it has some frame of reference, so some kind of global frame of reference we can think about for this robot. And so what we want to now do is we want to be able to construct and position the remaining links within this robot that we would need to sort of build up its full kinematic structure. So we could think about what's shown here as sort of being the base of the robot with the given frame. And so let's say that we have an arm, which is our box geometry, and we want to be able to position this arm correctly. So within this, we might say that there's, we have the 4 vertices, and we could pick out one of the vertices, for example, to denote this point. So we could say P sub link to denote the particular single vertex in the upper left corner of that box geometry. And so within this box geometry, as we were talking about on the last set of slides, it has its own frame of reference local to the link. And so what we have to do then is we want to figure out where this point, where this one vertex P sub link is within the frame of reference of the robot, so that we can position our geometry within the frame of the robot. And so to do this, we're going to use a transformation from the link frame to the robot frame in order to transform the vertices from our link into the robot frame. So the goal of this transformation is it should apply the following, right? Where it can actually position all 4 vertices of our link geometry in the frame of reference of the robot. And so in particular, this one, the link frame origin point would be expressed by this green circle, and it would be essentially corresponding to the transform that we talked about, where we want to transform from the link frame to the robot frame. So if we rotated and translated the link frame origin into the robot frame origin, we should arrive at the green point shown in the robot frame. And so how can we think about this in this notion of kind of relating these 2 frames as a transformation in steps? So we can think about it as first considering the link within its own frame, and then considering how it is we can transform that link frame into the robot frame, right? And so first, we can think about this as starting with an aligned set of frames where the link frame perfectly aligns with the robot frame. And we're then going to rotate our link frame with respect to our robot frame by our rotation matrix R, which we'll calculate. And then we're going to translate that link frame to be with respect to the robot frame according to our translation components described by the vector D. And at that point, we will then have created our transformation matrix that we need in order to calculate where the vertices of the link are in the frame of reference of the robot. So one thing I want to point out and kind of emphasize is once again that we always apply rotation first and then translation. And so the reason why that is illustrated quite nicely on this figure. So conceptually, what we want our transformations to do, right, is if we think about applying just a rotation to a geometry, we want that rotation to sort of rotate about the local axis and the local origin of our geometry, right? And so if we first applied translation and then we rotated, we would get the behavior shown on the left-hand side of this visualization, where you can see that our rotation, because it's applied after we've already translated the geometry, is about the sort of world origin and the world frame of reference as opposed to the local frame of reference. So our rotation is not really behaving the way that we expect when we programmed our rotation. Whereas on the right-hand side of the figure, we first rotate and then we translate. And the result is that when we conceptually look at how changing the rotation would affect the resulting composed transformation, it behaves like we expect, where it looks like if we change just the rotation component and leave the translation constant, the object is rotating about its own frame of reference and not the world frame of reference. So this makes it much more, much conceptually nicer when we go to implement our transformations, where we sort of know what behavior to expect and we can reason about it in a kind of clean manner. So how do we extend these ideas that we've been talking about in terms of rotation and translation transformations into 3 dimensions? So the answer to that is we essentially extend our transformation matrices into 4x4 homogeneous transformation matrices. So in the top here, we're showing what a three-dimensional translation would look like, and then on the bottom, we're showing what a three-dimensional rotation along just the z-axis would look like. And so once again, the one thing to point out is that in this 4x4 homogeneous matrix, the final element in the lower right-hand corner will always be 1. Will always be set to 1. And so on that last slide, we defined just rotation along the z-axis, but we can define similar matrices for rotation along the x-axis and along the y-axis, which is shown on the right-hand side of this slide. So you can refer back to these. And the way that these are derived follows the basic principles of trigonometry and geometry. So you can work through those as an exercise on your own in terms of how these matrices were derived. And so bringing these together, when we then want to compose our rotation followed by translation, one way that we could implement that would be as follows, where we'll first rotate. So the way to read these is to read from the right to the left. So we rotate first about z, then we rotate about y, then we rotate about x, and then finally we translate. So these composed transformations in homogeneous coordinates exist within the special Euclidean group 3, when we're dealing with three-dimensional transformations, where the rotational component is in special orthogonal group 3, and then the translation component is a vector of real 3. The other thing then that we are going to sort of now talk about are how we can use this notion of composing transformations to build up our hierarchy that of transformations used for forward kinematics. And so what we're going to look at here is we're going to step through how we can construct our example robot based on traversing the kinematic tree that defines the robot and composing transformations along the way in order to position each link and each joint within the world coordinate frame. So as we read the kinematic structure, which is shown on the left, I just want to point out that each arrow you can think about as representing a matrix transformation that we need to implement, which is going to transform the child where the arrow is pointing with respect to the parent, where the arrow originates. And so how is it that we're going to be able to compute these matrices in order to arrive at our transformation for each part with respect to the world? Well, the answer to that is forward kinematics, and in particular, we're going to be using what's called matrix stack recursion, which we're going to walk through now. So ultimately, the goal of this portion of the lecture is to discuss how it is we can compute a transformation for the pose of the end effector in the world coordinate frame. So we can think about that as being kind of the ultimate output of our forward kinematics. And so once again, so the way that we're going to implement this, and what we're going to walk through now, is how we can implement forward kinematics with what's called a matrix stack, where we're going to recurse through the tree and build up our matrix transformations. So the overview of this process, right? So the goal, once again, is going to be to compute a transform of the frame of reference for each kinematic node with respect to the world coordinate frame. And so the approach we're going to use is we're going to compose the transformations as we traverse the kinematic tree using a stacked data structure. And so the stacked data structure is what's going to allow us to sort of maintain a sort of memory about where we are within the tree and which transformation we should be using as we try and build the next transformation. And so we're gonna step through this. So the code for this is going to essentially look like recursively iterating through the branches of the tree, where we're going to alternate between each link and the corresponding child joint in order to update the current transform that we're sort of working with in memory. And then we're going to store those transformations within the tree so that our simulator knows where to visualize the robot. So we'll start with the base link. So we're going to start at the root of the tree, and then we're going to essentially iterate down each branch in a recursive fashion. So let's step through this and see what this looks like. So we're going to start at the root of the tree, which is the world coordinate frame. So this you can think about as being the global origin of the world. So it's this sort of center of the world. And so to start with, we're going to initialize our matrix stack with just the identity matrix. And so the top of the stack can be thought of as the matrix transformation that we would need to apply in order to form the frame of reference of the current node where we are within the kinematic tree with respect to the world. And so in this case, since we're just starting out, you don't need to transform the world frame at all in order to arrive back at the world frame. Hence, we start with the identity matrix. So at this point, then, what we're going to do is we're going to traverse to the child, which in this case, based on our setup of this kinematic tree, is still within the. You can think about it as being like a joint, but it's kind of an empty joint, just for the sake of our of kind of keeping our recursive function usable in this framework of going from link to joint. So you can see we push another identity matrix onto the stack, and at this point now we are going to begin working with the actual origin of the robot. And so for this for this, what we can do is we can use the properties within our robot object in order to construct the transformation for the robot origin with respect to the world origin. And so first we're going to compute the translation for the robot's position with respect to the world based on the XYZ property of the robot origin. And we're also going to compute the rotation matrix for the robot's orientation with respect to the world based on the origin RPY property. And so composing these two transformations together by rotation first and then translation will give us the robot's position and orientation in the world. And so at this point, we can then multiply this new transformation with our top of the stack in order to arrive at the X-form property for the robot. So we've now computed this, so we can store it into the robot origin.xform. One brief tangent is I just want to mention that the order, so we're going to be working with Euler angles in this class, which is just a way of representing rotation matrices with respect to each individual axis component. And so one thing I want to mention is that there are different ways in which you could choose to order the rotations about the different axes. And the order in which you choose to use will affect the actual resulting rotation. And so for this course, we're always going to use what we call the XYZ order, which means you first rotate about X, then you rotate about Y, and finally you rotate about Z. And so once again, remember to read from right to left when you're thinking about these matrix operations. Okay, so coming back to our matrix stack, so we now have this. So we now have the first transformation here at the top of our stack. So we're going to recurse to the child link, which is the robot's base. So once again, one small tangent is that within our is that what we have here on the left is link 1, but we can actually think about this as being link 0. It is the base of the robot. The reason that we're making this distinction is because we want to stay consistent with the Spong textbook, and so that's the reason for this brief divergence. But link 1 you can think about as being the base of the robot. So at this point, link 1, because we haven't transformed it yet, has some origin that overlaps with the world origin. And so our job now is to figure out how to transform link 1 such that it will be positioned with respect to the world origin correctly. And so link 1 has a set of vertices, right, that define the geometry for this link. And so we want to be able to transform those vertices into the correct position in the world coordinate frame. And so to do that, what we can do is we can use the top of our matrix stack as a sort of reference that we can use to build up this transformation. So in particular, if we take the top of our matrix stack and we transform the vertices of this first link, what we'll do is we'll be positioning that link with respect to the world origin frame as it is intended. And so by applying this transformation, then we can position our link correctly. the next step is we need to be able to position let's say joint 1 to start with, correctly within the frame of the world. And so to do that, we're going to recurse down to joint 1. And because we traveled along an edge, we know we need to create a new transformation matrix. And so to do that, we take the properties of this particular joint, which is the XYZ and RPY. Once again, we can construct a translation and rotation matrix, which is D sub 2 and R sub 2, both with respect to link 1. And composing those two transformation matrices will give us the local transformation for traveling from the link 1 frame to the joint 1 in link 1's frame. But then we also need to compose that with link 1 to the world transformation, which we calculated before, in order to calculate this composed transformation that takes us from joint 1's frame to the correct position within the world frame. So at this point now we can store what's now at the top of our matrix stack within the robots.joints of joint 1 X form, and this now will allow our our process to continue. So once again, we recurse to the child link of this joint 1. We arrive at link 2. And so now we need to, once again, calculate what the transformation for link 2 should be in order to position it correctly within the world coordinate frame. And so to do this, we're going to follow a similar process where we will take the top of our matrix stack, we will multiply it by the vertices of link 2, and that will give us the correct positioning of link 2 with respect to the world coordinate frame. At this point, we try to recurse further down this branch, but we reach the end of the branch. And so what happens is our matrix stack gets popped until we arrive back at link 1. So we're going to pop the top off of the stack, and we arrive back at link 1. And you can see the nice property about using this matrix stack is it's using our memory so that we don't need to go back to the very start of the tree and rebuild portions of the transformation matrix. We remember what the transformation matrix for link 1 with respect to the world is, which becomes now the top of our matrix stack. And so now we can continue this process of recursing down the second branch of the tree. So we'll recurse down to joint 2. Since this is a joint, we need to calculate a new transformation matrix. So to calculate the new transformation matrix, we can use the properties of the joint in order to calculate translation matrix D sub 3 with respect to link 1 and rotation sub 3 with respect to link 1. We compose those with the top of the matrix stack, and we have this new transformation matrix for joint 2 with respect to the world, which is now what's in the top of our matrix stack. And once again, we can now recurse down to the child link, which is link 3. And once again, we can now use what's in the top of our matrix stack to transform the vertices of link 3 correctly into the world coordinate frame. We can then recurse down to the child joint. So this is now joint 3. Because it's a joint, we need to calculate a new matrix transformation, which we can do using the same process, position joint 3 in the world, and then position joint 4 accordingly. And at this point, since we've reached the end of the branch, we'll pop back. We'll continue to pop back since there's no more children of these links until we've reached the back of the root of our tree. And at this point, we will have completed our forward kinematics, and we will have positioned the robot in a valid configuration within the world coordinate frame. And so with that walkthrough, that now covers how it is we can compute the transform for the end effector with respect to the world coordinate frame, because we will have positioned every link within the world coordinate frame. And so that covers our walkthrough of forward kinematics. And so coming up in the next class, what we're going to look at is how to represent motion due to the joints being articulated. And so this is going to include translation and rotation about arbitrary axes, which is kind of foreshadowed by fidget spinners, believe it or not. So next class we're going to talk about how to implement these with quaternions and axis angle rotation, and some additional tips and pointers for getting started with Project 3. And so with that will conclude our lecture for today. Thank you for watching, and I look forward to seeing you this week.